Silicon technology for semiconductor manufacturing was 4 inch. Then it has gone to 8 inch. Today's is 450 millimeter, almost 1.5 feet diameter. Now that means silicon wafer, if you want to deposit some ICs, these, that, on this thing, it becomes feasible only when you have large area for deposition and all this thing. So this companies, there are various companies which are making this product. This is called inductively coupled plasma system. We have made some efforts at IIT Bombay to develop this technology. I will not go through these details, but basically you have the RF generator which is going through this LC network. Current is divided by these two capacitors. There is one inductance coil, there is another inductance coil, and they are grounded through the capacitor. Again, they are for different electrical requirement. There is a quartz plate through which the RF can transmit. Then there is another quartz plate that is mounted onto the chamber. Then this one is used for getting rid of the direct coupling of the RF fuse with the dielectric. See, this is the situation. You have that those antennas, cylindrical antennas, quartz plate, then metallic shield, Faraday shield, then another quartz plate, and here we generate the plasma. Now, rather than going into detail, I will just show you the inductively coupled plasma facility, which will generate the plasma on 8-inch diameter and with absolute uniformity. Okay, and this is in metallurgy and material science department at IIT Bombay. We have developed indigenously. If you buy this component, it will cost you 2 crore rupees from abroad. This is an indigenous development that we have done at the cost of 40-45 lakhs rupees only. We were supported by that funding from DST, and it's working very well. Okay, this is how your plasma looks like. 8-inch diameter of silicon wafer can be processed for solar cell deposition, etc. Amorphous silicon again. There is another unit that is developed for reactive ion etching, because when you want to make the MEMS, etc., you need to etch those silicon wafers. So this cryogenically cooled reactive ion etching facility, against similar version of what I have shown you earlier, that is developed. These results are only to show you how uniform is the plasma, these plasma parameters, etc. Electron number density, you see from in the center on 20 centimeter diameter, that means on 8-inch, the number density of the electrons in the plasma is very uniform. And again, there were questions raised, okay, these are all measurements, what about the actual this one? This is the one which is silicon, amorphous silicon thin film is deposited using inductively coupled plasma. With the same facility, results are published here in IEEE transaction on plasma sciences. And this is on 5-inch diameter substrate, amorphous silicon. You see the uniformity of deposition. Thickness was measured, 400 nanometer, 402, 401, 402, 400, 400, 400. Okay. Non-uniformity in the coating is only 0.5%. For commercially available inductively coupled plasma system, the non-uniformity falls in the range of plus minus 4.5%. Our unit that we have developed is giving 0.5% for the facility that is developed indigenously. So this shows like the capabilities that are required to be done, and with the particularly with the semiconductor manufacturing taking off now in India, you cannot rely on all components that are imported from abroad, particularly for some components which are required for some specialized application. It's impossible to get that technology from abroad, and in an organization like where I was working with Bhabha Atomic Research Center, it's impossible to get even radio frequency generators, because they know that it is going to be used for nuclear research and they don't want to give to you. Oh. In the nuclear devices, it is at plutonium, and the plutonium is a neutron emitter. And if there is a theft then of this material, then it's a very dangerous thing, because somebody can escape with the plutonium from the airport, and there's a national threat. So basically, you need to have these safety devices. So you must have the neutron monitors. So we are developing something on this semiconductor-based neutron detector, so that the neutron detector can be of the size of the cell phone, and in the security, with the security people, both in the atomic energy establishment as well as in airports, etc. These devices can be used. So basically, here you have the semiconductor, PIN diode, and in which there are trenches. This typical trench size is 4 micron by 4 micron and depth of 25 micron. That is the one on which we are working. Then on this, in these trenches, you fill boron carbide. Again, this boron carbide is filled through chemical vapor deposition during plasma process, and this boron carbide, once you fill into these trenches, it has boron 10, which interacts with your neutron, which gives you lithium and alpha particle. And alpha particle being energetic, this alpha particle generates electron ion pairs into that p-ion junction. And these electron ion pairs are then attracted across this electrode and this electrode, and you get the pulse. Like each neutron encounters with the boron 10, it gives a pulse, so you can detect the presence of the neutron emitter in that region. So this is basically, again, if the pillar size goes down, the efficiency can go up. So this is the scenario. You have P plus layer, intrinsic layer, and then N plus layer, boron carbide is filled inside this, and these are the contacts. Actually, they are made. So basically, this is the facility that we have developed for this particular application. We use, this is a radio frequency plasma, which I have discussed with you. So this is the plasma chamber in which that those electrodes are there, and onto which we mount that p-ion junction assembly. And then the precursor is decomposed by the plasma medium, and it gets deposited there. This is the process that is going on. This is the precursor that we use, orthocarbon, which is a giant organic molecule, C2B10H12, with a sublimation temperature of 80 degrees centigrade. So when it sublimes and decomposes into the plasma, you get boron containing radicals, carbon, and all those kind of things. So what you deposit is boron carbon containing phase. Okay, so this work is going on. Okay. This is the one example I am showing you. Like this was the project that we did long back with Institute of Advanced Studies in Science and Technology at Guwahati to develop corrosion resistance coating on the bell metal components. See, bell metal is a material something like our brass, and in the northeastern part of the country, there are large number of small scale industries. They make all these iodols and all those kind of things. And if they want to have the market, they are exporting these things to the outside world. But earlier, this lacquering, like putting turpentine and all these things, was allowed. Nowadays, it is environmentally banned, and if you are putting the turpentine coating, you cannot export it. So basically, there was a necessity to develop the coating on these components using this plasma process. So we have done that on this. See, these are the acid clean components. It is how it looks like. This is a hexamethyl disiloxane plasma coated component, and this is the one which is again by plasma process polystyrene coated. So polystyrene was decomposed into the plasma medium, and then and again once it is deposited, the corrosion test and all those things, they were done. Okay. So on this, we have also been awarded a patent actually by the government of India, and these are again the components. Like this is how it gets corroded because of the moisture and all those kind of things, oxidation. Then hexamethyl disiloxane coated, and this is a polystyrene coated component. And this process has been also transferred to some industry. Now I am just showing you one example again. PET bottles. PET bottles, these are PET, your plastic bottles. Okay. Now this example is again from Germany. Now They are using, see, their requirement is very heavy because Germany is the country where everybody is drinking beer actually. Now, to give maximum satisfaction to the customer, it is essential to have packaging that can protect sensitive food from going bad due to contact with the atmosphere. In the year 2000, around 120 billion bottles were made of PET that are in the country like Germany. And Germany is of the size of Maharashtra. So imagine the market in country like India. Now PET market is going at the rate of 10% annually. But what happens? PET allows too much of oxygen to diffuse into the penetrate through the pores, and too much carbon dioxide to escape. So you have some carbon dioxide containing liquid. So carbon dioxide is also to. So that means if you are storing beer into this plastic container, then it will go flat and begin to taste bad actually. So plasma technology offers a very good solution for this. It brings out a revolution. Amorphous carbon coating on the internal of these bottles can be given by immersing this in the plasma, by making this as the cathode with the negative bias. You decompose that and that will make amorphous carbon coating on the interior, and it's carried out in low pressure plasma CVD process. Thickness of the carbon coating is barely 100 nanometers, 100 into 10 to minus 9 meters. And the barrier properties are improved by 30 folds, okay, by such a small thin coating. Another procedure that involves is layer of SiO2 that is formed on the outside of these bottles, and this enhances the barrier properties by a factor of 4. These are from the data again. Advantage of PET bottles with this SiO2 coating is that it remains as clear as glass in contrast to the milky white that appears when the amorphous carbon is coated. And such coated bottles have become a genuine competitor to the glass bottle, and around 300 beer bottles are required per year in Germany itself. That was the data from 2000. Imagine we are in 2025 and every year market is growing by 10%. So imagine how many bottles are required there now per year in a small country like of the size of Maharashtra. Okay. Now I think this microwave discharges, again micro is the energy which is your radio frequencies which are 13.56 into 10^6 hertz frequency. Microwave, they are having few gigahertz. The one you are using in your microwave oven is 2.45 gigahertz, 2.45 into 10^9 hertz. That is the frequency of the radiation. So these microwaves can be used for making the discharges again, for making the plasma. Its effect is electrodeless discharge can be produced, high degree of ionization, wide pressure range from atmospheric pressure to subatmospheric, high electron to gas temperature because non-equilibrium plasma, low sputtering by the incident time, can be sustained for longer duration for okay, this is the one that I made into year 1992. Okay, now this is the one electron cyclotron general system that was made in year 2000 at BRC, and 8-inch diameter it generates the plasma. These are your microwave hardware. They are different components. They are brought here into the plasma chamber, gas at low pressure. Plasma is generated. Again, these substrates can be biased by RF power, and we use this facility for deposition of diamond-like carbon coating. Diamond-like carbon is nothing but an amorphous phase of carbon which has sp3 bonded carbon matrix in the amorphous phase, and in which there are sp2 bonded clusters, graphitic clusters, and that has very large number. See, this is how the facility looks like. And diamond-like carbon, the one which I just explained to you, it is having very good hardness, 10 to 25 gigapascal, low coefficient of friction because it's a smooth coating. So it gives very low coefficient of friction with the metal surface, high wear resistance, chemical inertness because it's a carbon coating, excellent biocompatibility. Most of the heart valves that were implanted into the patient, they were made of pyrolytic graphite, and on that the coating of diamond-like carbon is given. They are biocompatible. It protects the opposite rubbing surfaces from significant wear without using any lubricant, and it's a transparent to infrared radiation because for your military applications, for your germanium optics, night vision devices, these coatings are very, very important. And because of these extreme characteristics, they have attracted a lot of attention. Of course, I will not go through this. See, the again 8-inch diameter uniform plasma was obtained. We deposited some diamond-like carbon using this facility. Microwave power use was 400 watt. This was the base pressure. This was the operating pressure. Substrate was silicon 111. It was biased with a negative bias from 25 to 200 volt, and argon and methane mixture was used, and deposition rates were for almost 45 minutes. Coatings were golden yellow to black, grayish, insulating. Deposition rate was 0.2 to 0.7 micron depending on the process parameter. Hardness was 15 GPa, because 15 GPa is almost 7 times harder than steel. Steel is 2 GPa and gigapascal, and strongly adherent to the substrate and scratch proof. I will not go through this one. Okay. Now, this problem with DLC, it cannot be deposited on steel, because steel has a very high affinity for carbon. So for depositing this DLC onto this, we use this hexamethyl disiloxane as a precursor, and then it has a lot of carbon also, carbon hydrogen. So using that mixture, we deposited these DLC SiX films, and again they could attain hardness of 14 GPa, 7 times harder than that of steel. Its optical properties were studied. They are transparent in infrared region, because that is very important. You see the extinction coefficient beyond 600 nanometer is flat, almost near to zero. That means the coatings are absolutely transparent in the far infrared region, which is used for night vision devices. Okay, its mechanical properties, etc., that was studied. This is how the components were coated. Okay. I will show you one very classic example again, how this plasma technology can be used for making diamonds. Nowadays, you know that diamond is the hardest known material, and it is found in the like deep below in the earth, because of high temperature, high pressure processes. Graphite is converted into diamond, and that is the diamond that you are basically seeing from the mines, etc. But now the same diamonds can be deposited by plasma technology. Basic philosophy is, you have the methane gas, and this methane gas is decomposed in the plasma as carbon containing radicals and other decomposition products. And this process is activated by various like hydrocarbon hydrogen plasma before contacting it on the substrate, that is kept at 800 degrees centigrade. Around 900 is the optimum temperature, and all kinds of substrates have been used for deposition of this coating. Nowadays, even millimeter thick or centimeter thick diamond coating have been. There are companies now all over the globe that are working on this area. And why this again diamond? It's radiation hard, so you can make radiation detector. Excellent hardness, so you can make tools. Low coefficient of friction, so tribological application. High thermal conductivity is 4 times that of copper and silver. So in a high power electronics, to take out the heat from the circuits, the substrates are used. Transparent to electromagnetic waves. Excellent electronic properties, so you can make active and passive devices. And of course, these are the criteria under which you call this is the facility that I have set up at BARC for deposition of diamonds. These are all microwave hardware. Your magnetron that generates the microwave, etc. They are inside this cabinet. This is a chamber in which the plasma is generated, and this is how the plasma looks like. Like at a pressure of around 50 to 100 torr. See, basically in that cavity, you feed the microwave power, and by solving the Maxwell's equation, you have to design the region where there is a maximum focus of the microwave energy, and that is the region where you will form that ball size plasma. In that, you feed methane hydrogen, so it will decompose into carbon containing radicals, per hydrogen will decompose into nascent nascent hydrogen, and this carbon from the methane, which is decomposed, will deposit as both sp3 bonded carbon as well as sp2 bonded graphite. You don't want graphite, so you want to remove that graphite. So that is done by atomic hydrogen, that is generated because of the hydrogen decomposition. And typical composition range is 99% hydrogen, 1% methane. Okay, because you need very high abundance of or high concentration of hydrogen containing nascent hydrogen, which will take care of the sp2 carbon, remove that. Basically, it will do the etching of the graphite leaving behind the diamond. And these are the red hot substrates. Again, these are at 900 degrees centigrade. Temperature is again generated by the plasma itself. And you see, these are the diamonds that are deposited. These are basically the diamond crystals. And okay, these are continuous diamond films. And see, these are the diamond, these ones actually deposited. There are all these characterization like Raman spectra, typical of 1332 centimeter inverse Raman peak, etc. That was obtained, and then X-ray diffraction was done to make sure that whatever we have deposited is diamond only and not graphite. So basically, again, this same plasma can be used for carbon nanotube deposition. Carbon nanotubes, you must be knowing, some of you might be knowing, they have a very large number of applications in because it's the strongest solid actually. We have basically tried to utilize this in making the cold cathodes for various applications, but particularly for accelerators, electron accelerators, etc. It shows excellent field emission characteristics. It has also applications in supercapacitor development, battery electrodes, lithium-ion batteries, etc. So, because it has very high surface area, so these things are being investigated worldwide, and this is the one which we have developed in our laboratory. This is again, this carbon nanotubes grown on stainless steel substrate using the microwave plasma device. Our results are published into this particular journal. And okay, this I will skip because there is not too much of a time. This again, diamond-like carbon-coated metal hip implant. Like, see, when the hip implants are implanted into the human body, you need the surfaces which will produce very less friction. Because if the friction is too much, then it will generate the debris and it will create the adverse reaction into the body tissues. You don't want that. So basically, this ball and socket assembly, the balls are coated with diamond-like carbon, because once the diamond-like carbon is coated, its coefficient of friction is very low. So that rubbing of the counterpart will not generate the debris into the human system. So this is again deposited by plasma process, not by me. This is taken from the literature. Now, these are different. I was talking to you about low pressure plasma. I will just show you some examples. See, low pressure plasmas, they were dominating the scene, but for last 1 decade, there is too much of a development about, because people want these all advantages of low pressure plasma to be available at atmospheric pressure. That means the cold plasma property should be there in the plasma that is generated at 1 atmospheric pressure. Worldwide, like a lot of work is being done, because this has become a very active field, both in plasma medicine and all these things. Now, even your dental root canal treatments, etc., they are using these plasma jets. So, whatever pain was there in the patients because of drilling, that should go over in future, probably because of these plasma jets, etc. But anyway, that is not the topic of discussion today. These atmospheric pressure glow discharge devices that we have made, again, this is the one that we developed under BRNS project scheme at Guwahati Institute. And this is the electrode. Basically, this electrode was coupled to the radio frequency power. This is a 300 micron cut given onto the electrode, and this is spiral basically. And this is given at RF power is given to that. So at a given moment, both the walls of this slot, they are having the same potential, and the electrons that are trapped in between, they are subjected to the pendulary motion. They gain energy. Once they become energetic, they create plasma, and the plasma is propelled through this slotted portion. Now, this is how the actual plasma will look like, and through this plasma again, this is on the heated surface at 700 degrees centigrade. This was the upper electrode. This is my plasma that is generated at 1 atmosphere. No vacuum now. It's at 1 atmosphere. and these are the carbon nanotubes that were grown onto using this. Again, for these various applications, including field emission, supercapacitor, and battery electrodes, etc., they are being investigated. Okay, so these are the ones. These are all some of the publications that are in various journals. Then there was a need to develop the portable devices for various applications. And one of the application was cleaning of the plutonium decontaminated surfaces from the reactor. Because whatever comes out of the nuclear reactor, it has a lot of plutonium. And as you all know, plutonium is highly radioactive. And because it is radioactive, you cannot go even near to that, you know. But so the people who are working there, they are basically all these not very highly educated people who know that what is radioactivity and all these things. So it is the duty of the organization or duty of the management to see that the radioactivity is not too much where the operator will be exposed and all these things. So basically the objective is to clean those components that are coming from the reactor. So process was required for that. So we made some efforts. These are basically a atmospheric pressure glow discharge unit that we tried to made out of microwave power. And you see this is my picture of 2012 or something. This is a plasma jet, and this plasma jet, you see how much cold it is. Because I can just put my finger there, and on the finger it is there. So absolutely cold plasma was generated at 40 watt power of this one using the microwave hardware. And okay, we tried to go up to very high power into that, up to 200 watt. Then this is the jet that is. Then there were questions raised whether the devices that you have developed is safe, because it is going to be used by the people, and if there is too much of micro leak, then there is a problem, because even when you are using your conventional microwave ovens into your house, we should not go very near to the micro door and watch what is going on inside that, because there is a limit up to which the micro radiations leak is allowed, and that is 1 milliwatt per meter square. So at the operator location, the leakage level should be less than 1 milliwatt per meter square. If it is more than that, that means it is attacking your eyes, and eyes have a lot of water. Water, it gets heated up because it's a polar molecule, and it can generate cataracts into the oil. So don't go very near to your micro oven when you are using in your house. So similar questions were raised when we developed this technology. How safe is your device? So the leak detection is in progress is shown, and it is found that it is safe. Okay. Then it was taken, a process was developed for this, because again, when you are trying to remove plutonium from the reactor component, it has to be by some chemical reaction. And that chemical reaction was using argon, fluorine, argon, carbon tetrafluoride, oxygen, plasma. It generates oxyfluoride radicals, which are highly active. It attacks plutonium. It removes that as plutonium hexafluoride, which are vapors. Those develop. Like you have seen some of the bridges, etc. In some of the bridges, like when the pillars, etc. Suppose there is a degradation of the pillar, and the inside of the pillar, the steel, which is exposed to the saline water, it undergoes a lot of corrosion, and then the cross section they become very thin. Now you cannot dismantle the bridge and redo it again. So basically, some reinforcement is done. So that reinforcement is done. That means those steel bars which are there, that basically the corrosion layer is removed, and you put the metallic coating onto that. So basically, again, it is an art-based process. This is one electrode which is feeding the wire, metallic wire, and this is water-cooled another electrode. Arc is stuck between the two, and at the base of the arc, the temperature is very high. So basically, you see something like this. And now into that arc, you feed the wire continuously, okay? Metallic wire. So it will undergo melting, and by the splats, you can form the coating very easily. Now this is one example I am showing you again. These are graphite electrodes, almost 30 inch long, 13 by 9 inch or something like that. These are used in our fluorine cycle in EE or the very high current application. Thousands of amperes of current is to be fed to this electrode. Now on this electrode, basically if you are feeding such a high current, then basically with the graphite electrode, if you make the clamp or giving the electrical contact with the high current that is going through the circuit, there is a degradation here, and then that contact will come out. So basically, this is a nickel coating that is given onto the carbon block. That is called a wire arc spray process. And now this is a very routine process. Routinely, our people are doing that. Again, these are the microstructure. These are the bioceramic coatings of hydroxyapatite. That this was my work actually long back. There is no time, but see, I will just explain the gist of all these things. See, the dental implant that is implanted into the patient. Basically, what they do, there is a titanium 6 aluminum 4 vanadium root. The surgeon drills the hole, they put that titanium 6 aluminum 4 vanadium assembly into the jaw, and basically it is sealed. After 3 months, now if there is a coating of hydroxyapatite on this, hydroxyapatite is calcium 10, PO4 6, OH2. Now this is the mineral, this resembles to the mineral phase of the bone. Now when that coating of around 50 micron, not more coating, only 50 micron or so, that much coating is given. So basically your tissues, body tissues, they fail to understand whether it is the actual bone or it is the artificial bone. Because the mineral composition of that phase is identical to that of the bone. So tissues, they grow here onto this, and it becomes a part of your body, jaw. And then on the top of that, the surgeon is just like putting the top cap on that. This is ceramic, this one, so it becomes a permanent tooth. These are very expensive processes, and but now this technology is developed, but again it needs certification and all these things. So our surgeons, they were not having the patience. So, but the process is there, and people are using it. All over the globe, most of the laboratories, they are producing these implants nowadays. So this is the one that is done. Then okay, these are again the components that can be hip, ball socket joints, titanium 6, titanium 4 vanadium, coated with different ceramic materials. Again by this plasma spray process. These are again textile machinery components that are used by the industry on a routine basis. Then paper industry, the rolls etc. that are used in the paper industry, they undergo wear because of continuous operation. So they are coated with the ceramics by this plasma spray process. Then all these internal combustion engine components. See, basically, if any process or a combustion of the fuel is carried out at high temperature, then your efficiency of the cycle is more. But that to have higher temperature, the material should stand that temperature. So these components are coated with the ceramic, and again these combustion chambers, their inner lining is given the coating of ceramics by the plasma spray process. Again, this is the by metal wire spring, how the components can be restored, the corroded components. This is the repair procedure. Okay, this is how your low pressure plasma spray system or coating gas turbine blades, etc. Because most of the aeroplane industries and your turbine industry, they are using this process for coating their turbine blades. Because the turbine blades, they have to be coated by thermal barrier coating for reducing the heat loss on the heat onto your turbine, that metallic component. So ATS zirconia coatings are given, and okay, these are again consumer goods. They can be coated by plasma spray. This one, steel industry. See, most of the components they are used by this either high velocity oxide blend or plasma spray coatings. So okay. So this is where I think we should stop because there is not too much of time. I think it was very lengthy. So if you have any question, I will be able to answer.
I have one question.
Yes.
This technique can be used on the irregular surface of the metals.
Which one?
Any.
Yes.
Sometimes the metals having the irregularities like cracks.
Now, if suppose there is a component, metal component, in that there are some cavities, either holes or uneven surface, then you can make that component immerse into, you can immerse that component into plasma. Apply very negative bias, pulsating negative bias. That the process is called plasma source and implantation. And then you either do the coating or develop. So basically,
It is not efficient on the irregular surface.
no, there are solutions available. Plasma nitride, see the gear is very highly irregular. But now I have told you that still made screen, whatever screen is put onto the top of the surface, because that screen is made the cathode and that irregular surface will not see any potential. So basically, nascent nitrogen and hydrogen that are produced, they will do the reaction. And it's producing on gears and etc. They are very highly irregular components, irregular shape. So there are solutions, and those solutions will come only through research. Earlier, plasma nitride appears to be very simple, straightforward thing, but people realize when there are small holes or cavities, they form the narrow section and the electrons that are trapped, they become highly energetic and they hit the component and create arcing. So to avoid that, that active screen plasma nitride has come, and now the results are okay.
Okay, sir, I have one question. Can we use this technology in additive manufacturing?
Additive manufacturing, I have seen some work on the wire spray. The one which I have shown you last time, like where the wire is continuously fed and all. See, in 3D printing, etc., what you are doing, basically all the material that is put layer by layer and then you put this one and develop your component. So this is again the similar thing. There are some efforts now to use this for additive manufacturing. But because that I have not worked in that area, so I have not talked on that particular thing actually. But see again, people are using laser beam for additive manufacturing. You have the metallic powder which is put there and the laser beam to melt and develop the particular shapes and all these things. Same thing can be used by either plasma spray procedure or even your low pressure plasma spray, including using liquid precursor. Where the liquid precursor, you feed the liquid precursor, get them evaporated, and in a very controlled manner you develop the coating. But I have not worked in that particular area.
Sir, I have one question. Regarding insert, for those insert, we require coating. So which process we can use for that?
Actually, this most of the like titanium nitride coatings and all these things, yellow coating that are given, they use plasma CVD or sputtering.
PVD or CVD?
Mostly PVD people are using because CVD the issue is, as I have told you, see titanium tetrachloride hydrogen ammonia mixture. They produce very good quality coating, but small amount of chlorine that is trapped, that can create disaster. So rather than that, people are going through PVD route, cylindrical magnetron, okay? Use butter, titanium aluminum material in the nitrogen plasma, and you have the titanium aluminum nitride coating that is deposited on the. In fact, I do not have the slide on that, but we did some work while depositing the super hard coating using Patil, and the 40 GPa hardness using titanium aluminum nitride, boron nitride coating is produced by PVD, physical vapor deposition against Patil, basically cylindrical magnetron Patil. That could withstand temperatures up to almost more than 1000 degrees centigrade. More than 1000 degrees centigrade. So, and most of the industry, there are a lot of industries around, Pune and all these things. They use PVD. CVD can be used, but the control has to be absolute. CVD can in fact give you coatings even at lower temperature, but small amount of chlorine can be a disaster. Okay? So thank you very much.
I have one question. Sir, we produce diamond from these processes.
Yes.
Then that diamond having same quality or same properties like next diamond?
Yes. There are now lot of companies working in this area, and in fact we were the beginners actually in India to work in this area. In BRC and even in IIT and all these things. Some of the IIT faculties left and joined somewhere in the company. They have their own company. Many companies they approached to us whether we could help you.
Goldium company is applying this process.
Huh?
Goldium company.
No, there are many companies actually. And now they are commercially, they have the reactors, the similar reactors that we have shown you actually. But being in the government organization, we could not interact with the private companies and we could not do any understanding with them. But after I joined IIT, I gave, like when they approached me, I told them you sign a MOU with IIT and then we can become part of you. But they again don't want that because they don't want IIT to be part of that. This one, they want me to come there and do something for them, but which is not possible. So this is the scenario. But now almost 10 millimeter thickness diamonds are being produced, and it is very difficult to differentiate whether it is diamonds produced by the CVD process or diamonds produced on the mine. So, and India has taken a very big, because here we have the cheap labor, and at least I know there are few companies in Bombay itself. One company has 150 reactors. 150 reactors like this in one place. And day and night the production is continuing. But I don't know what will happen with the US policy of tariff now. How diamond export and all this thing. That business, we don't know. But yes, it can be produced. Okay? So thank you very much.
Thank you, sir. Take a seat, sir. I'm not HOD. I'm a listening I'm not HOD. Because I came from BARC, not originally from there. And where have been visiting for the last 11 years. First of all, I would like to thanks to Dr. D.S. Patil, sir from IIT Bombay, the senior professor and visiting faculty working as a visiting faculty, Department of Metallurgical Engineering and Material Science, IIT Bombay. Sir, in this session you have explained the work. I think this is your totally research work. And mostly, yes. Yes. No, not total research. Yes, part of my research work. and throughout this session we got a lot of knowledge. So thank you for that one. We understand deeply the plasma, what is plasma, and how we can implement throughout. You show the pictures. In various pictures, we found that you have done machines which measures the frequency of plasma. Also, how the plasma works. What are the major parameters that are considered while performing the plasma operations, and these all the things are most important for us to be here and to use them in our future. So thank you so much. Thanks to our Department of Mechanical Engineering, HOD SS Patil sir, who organized this FDP and invited you also for delivering the speech and sharing your knowledge with us. I would like to thank all the faculties who attended this program seriously, consciously, and they are listening throughout the day. Since last, I think 6 to 7 hours, they are sitting here and listening continuously. So I would like to thank to them also, and the organizing team, the supporting staff, the cameramans, the video makers, and those who are continuously working with us. Thanks to all. This is all about today's day. We will meet tomorrow in session 1 of day 2. Thank you so much.